I do that was really cool, and you were like, oh, maybe you weren't like, oh, but at least you pondered. A cubed root of 122, and I got it to within thousandths, tenths, hundredths, yeah, within thousandths of the right answer. But how did I do that? No, it's not magic, it's math, and not even hard math. What kind of math was it? Oh, well, this isn't working. Okay, hold on, give me 1 second. No! It was one of the driver cards that we did. All right, AJ, all right. What math did we use? A tangent line. A tangent line. Because a tangent line, you can solve for the y of a tangent line. We call it L to be our linearization, to remind us that this y, L, is different than the y of the original function, f. So y equals f of x is one function. Y equals L of x is the tangent line that's going off the function at one point c, f of c. We have to do f prime of c because we need the slope at that one point. But then who's this a guy? It's the guy I'm approximating. So yesterday, I did not know the cubed root of 122. I had to do some math to approximate it. I did not know him, but what did I know? Pretty close. Pretty close. So then I was like, oh, okay, well, if that's pretty close, then I'm going to use this as my point of tangency. Why? Because I know him. So when I went to plug in, I could do minus f of 125, not 122, but 125, equals f prime of 125 times x minus 125, all for the purpose of, wait a minute, 125? But yeah, the cubed root. So that's my function. So then I was able to say, oh, I know the cubed root of 125. And then I know the derivative of the cubed root of x. That's bring down the 1/3 and then make it a negative 2/3 of what? Of 125. And then x minus 125. Now hold on, we're supposed to be able to do this by hand. What on? Or would it mean the exact same thing if we cubed it and then isn't either way a 2/3 power? So what's the cubed root of 125? 5. What's 5 squared? 25. What's 25 times 3? 75. And then I went ahead and I said, oh, wait a minute, what am I supposed to be using this tangent line to approximate? Yeah, so then I said, I can change my x for 122. And technically, according to our formulas. But I think the math would also lead you there. Eventually, you're going to have to add the 5 to the other side. This is going to be my tangent line approximation, plugging in 122 to my tangent line. I apologize. My tangent line approximation. I can say equals for that, but I can say this is only approximately f of 125. Sorry, 125. This is approximated from the tangent line. I plug it into the tangent line. I don't know how to do that, but I know how to subtract. Ha-ha, negative 3 and divide. Ha-ha. Negative 3 over 75 is negative 1 over 25, and 5 minus 1 over 25. 24 25ths, and maybe just a couple of you remember. That was the very good approximation I got yesterday. What did I use? Tangent line. To do what? To approximate. Approximate what? Well, the thing I didn't quite know at the beginning, but I knew something close. And that's what tangent lines are good for. Tangent lines are good for, oops, let's go forward a page, approximating close to the function, close to the curve. Now guys, what if I was doing like the square root of, let's see, what's a good square root to say? The square root of 19. Square root of 19. Still only 3 off. 122 to 125, 16 to 19, because I know the square root is 16. Do you think that's going to be a better approximation or a worse approximation if I use it? Why worse? It's still 3 off. What's the nature of, what's the graph of any radical function? Let's just do like a square root. What's the graph of a square root? Yeah, Grace showed it. Do you guys remember it? Come on, show me. Right? It starts at a point and then it, whoosh. Okay, follow it. Doesn't it increase, have a lot of increase, and then what's it start to do? So, okay, so between 1 square root, or 1 squared, 4, 2 squared, 9, 3 squared, 4, 16 squared, 16, 4 squared, 25, 5 squared. There's a lot of change going on, but then it starts to level off. As you get farther down in any radical function, change means less and less. Now, if I was doing something like 172, yeah, this would be way off. But 3 way up here means a lot less because those tangent lines are skimming a lot more than a change of 3 would have made way over here. Does that kind of make sense? So a tangent line and where it is, this tangent line, the curve's going to only be near it for just a little bit. But this line, well, the curve's going to be kind of near it for a while. Does that make sense? So anyway, the behavior of the graph will kind of determine how good of an approximation it is. But that's only helpful if you guys are trying to make up problems to wow people. Otherwise, you don't really need to talk about error and how far off you are. It's more of an understanding that, like, hey, this one was super, super close. Why? Because you're only 0.1 off. Well, why didn't they go 3 off of this one? Well, 3 off is square root of 4. Like, that's a whole nother square root. That's not going to be so hot. So sometimes you're going to be really close, having been really, really, really close, like 0.1 off. And sometimes you can still be close, being like 3 off. But that's only because of the nature of the tangent line and how well it's skimming. But that was all the tangent line approximation. We ended here, and I was a little bit bummed that we weren't able to do better examples. But I think at least in the first 3 sections of homework, there was a video. Maybe that was assigned and maybe that wasn't. That would have explained how to do those sections. So let me see what you guys learned last night in homework. Notes open. Here we go. Example. Let's see what you learned from homework and make sure that you learned it right. This one says you have a function, y equals square root of x. Find dy and delta y. dy and delta y. Help me out. How do I find dy? Let's start there. I'm going to make it blue because it's blue on that side. How do you find dy of a function? Derivative. Good. Because the derivative of y is dy dx, technically. And what's the derivative of square root of x? Bring down the 1/2. X to the... Yeah, I was going to say x to the negative square root in the denominator, but I think some of you were just trying to go straight to the answer, and that's okay. But that's not dy technically. What does dy do? Good, multiply by dx. That's it? Yeah. I mean, that's the formula for dy. Do we have to plug in stuff? Yeah. Can we? Sure. We can plug in and say, okay, do we know what x is? Do we know what delta x is? So we can go ahead and just plug in and say, okay, 1 over 2 root 4 times 3, which will end up with 3/4. Yeah, you guys agree, right? dy equals dy equals. What does that symbolize? If I was to get up here a graph of square root of x, and if I was to make a tangent line at x equals 4, now 4 is going to be way down at 16. So pretend we're going by, I guess we can go by ones. 1, 2, 3, 4. But my y's would have to go by like 4s instead. But anyway, long story short, there we go. If we draw that tangent line, if we go over 3 and up, that change in y of the tangent line, that change in y of the tangent line will be 3/4. If I was to go over 3 more, it's a little hard to see right here, but if I was to go over 3 more, the change in y of the tangent line would be 3/4. Now, I wonder what the change in y of the function point to the function point would be. See, delta y goes from function point to function point. dy goes from point of tangency to other point on tangent line. But we can just use the derivative to do it. So let's do delta y. Now, I did delta y, and I was like, oh, f of x2 minus f of x1. But here's the problem, guys. Wait, do we have an x2 and an x1? Not exactly. So how do we get 2 different x's if we only have 1? Don't we have a delta x? Oh my goodness gracious. What does this look like? Limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. What equals that? F prime. It's the definition of derivative, which says, oh, hey, you can do a change in y if you have an x and a delta x. Oh, so what are my two y values going to be? Well, the one at 7 and the one at 4. Why? Because if you go from 4 over 3, aren't you at 7? Does that make a little more sense with the definition of derivative? It was saying, give me one x, and then we'll go over and get another x to have our two y's. But how do we solve for this? Uh-oh. Do you guys know this guy off the top of your head? Why is y nice? I can solve for him because I'm only having to use the nice point whose root I know. If I go doing delta y, all of a sudden I'm dealing with a root I don't know. And how do we know what 7 is? Square root of 7. Oh man, go do a tangent line approximation. Or say, wait a minute, take these two and compare them, and guess what? They're going to be approximately the same. Now, are they going to be exactly the same? No, because you had to go 3 away, and in 3 away, that tangent line diverged at least a little bit from the curve, so it's going to be a little bit off, like this one. They have the exact same delta. Let's see if I can get a color that's not blue or green. They have the same delta x. Actually, nope, that's the tangent line. This would technically be dx, and this one would be delta x. But what do you guys notice about the over? They're the exact... supposed to be. They're supposed to be the exact same. Doesn't matter the dx, the delta x, which is why we can always say, hey, they're the same thing. What's different is to the function, whether you're going to the tangent line. They'll be a little bit off, but they'll be about the same, about right. Why am I saying that? Well, what does dy actually symbolize? The change in y. Don't we know what the square root is? So if change in y is about 3/4, can't I say the square root of 7 is going to be about 4.75? Calculator time. Who has their calculator? What's the square root of 7? Is it 4.75-ish? And as you guys do that, it actually asks to sketch. So let me go ahead and do 0, 0, 1, 1. 4, 2. Okay, what do we get? Uh-oh, for the square root of 7? Oh, sorry. I added to 4. That's silly. Square root of 4 is 2. We should have added to 2. 2.75. Okay, so my guess for root 7 from this would be 2.75. But Thomas, what did you say it actually is? 2.645. Etc. ... So it's pretty close. But this d value would be, so we could be like, okay, so the square root of 4 is 2. 2 plus 3/4. I don't know why I did 4 plus 3/4. I'm sorry. 2 plus 3/4. 2.75-ish. I mean, it's not perfect, but is it close? Yeah. And if you were to do a delta y of 2 or a delta y of 1, you'd be even closer. Approximation. Go ahead.
So how did you guess 2.75?
Because delta y is approximated by dy, and delta y says, how far off is the future from the past? How far off would root 7 be from root 4? And so when I see dy is 3/4, which is about how far off, I can say, well, if I know this one to be 2, how far off would this one be? About 3/4, so 2.75. See it? So what we were trying to think of is, what's this guy? We knew it would be perfectly 4, 2. I mean, of course, we know this guy 1, 1, but we're not using him to get to 7. So when, did homework ask you to sketch anything, guys? Okay. When they ask us to sketch, what we would technically be doing is making a tangent line, and this should be a little bit lower. And the tangent line needs to go, there we go, all the way up to 7. If it lets me, I technically started it a little bit too high. You guys saw me trying to like compensate. There we go. So this 0.75 says, okay, as you go over 3, my dy, I go up 3/4, but that's to get to the tangent line point. And my delta y says, as I go over 3, I'm going to go up square root of 7 minus 2. Now, I don't know what that is, but we did know 3/4. We can say, okay, this point, since we don't know this change, this point is about 3/4 higher than the previous point. So my y is going to be about 3/4 higher. So I don't know exactly, but I can say this point is approximately 7 and 2 3/4. But they don't usually have you use the dy to actually add to the previous. I was trying just to give you a little bit more context. But the long story short is, which math is easier? And which one can you do by hand or in your head? This one or this one? Yeah, exactly. Just like a tangent line. I can't do the cubed root of 122, but I can do the cubed root of 125 and use a tangent line to get close. Use a derivative to get close in a tangent line application. Same thing here. I don't know exactly what the change is between root 7 and root 4, but I can take a derivative and plug in and at least know it approximately. This build is up to the idea of error. Help me out though, kiddos, in homework. Was there anything to do with error when you guys got to the word problems? Oh, that's right. What were you supposed to do up to last night? Up to the word problems, maybe trying 1, right? Where did the word problem start for you guys? Wasn't it like after 3 sections of homework or something like that? Like there were 3 categories and then word problems started? Does that sound about right? You guys said 28? 36. Yeah, 28 was like a, hey, here's some work. 36 was your next one? That one was like a, how do you see it? What was your next one past 36? 41. I don't think you really had word problems either. Was I nice and didn't give them to you? So you guys skipped over 31, 32, 33? Well, you know why I'm mean, right? Because the AP guys are mean.
You know who's not a bully?
Sorry that you had to carry it. Thank you, though. I appreciate it. Hannah, tell Richmond that I will tell him face-to-face thank you later. Whoa! That was just recorded.
You said that.
I don't want to know. Okay. You guys don't have any homework problems, and that's why I was asking. Thank you, thank you, thank you. You guys don't have any homework problems like these? I thought I gave you at least one, but man, I didn't give you any. I haven't ever seen one on an AP exam. That's probably why I skipped over. So I guess I should have just told you to do all of homework. Yay! Oh well, that lets you guys have a little bit of grace and not need to totally finish everything when you turned it in today, which most of you probably appreciated. But what does that mean you have to do tonight? So hold on. The one that you guys probably didn't get to, because you probably stopped whenever you saw the words on number 36, was just looking at a graph, but that's okay. Only minimal judgment. The one I saw after that had something to do with the 4th root of 624. I'm not going to solve this with you, but it just says use a tangent line to approximate that. But who's my F? Who's my tangent point? What's the X? They didn't give me all the nice directions from the early problems. But wait, isn't this what I did in class with the cubed root of 122? And you guys just helped build the problem. So the problem, they want you to approximate this as you guys finish homework if you haven't yet. How are you going to build the problem? How do I do a tangent line? Yeah, that part's not too bad, right? F of C or F of A, whatever. I'm just doing the general one first, Thomas. Okay, I need stuff to plug in. So I guess, who's my function? Fourth root? Sure, we can do that, right? Okay. What point of tangency do you think? Do we know the 4th root of 624? No, but what do we know? 625. And maybe not everyone knew that, but what is the 4th root of 625? 5. So I know. It's okay.
I don't know.
No. The powers of 4 also, to some extent. Because, I mean, maybe not the powers of 4, but you know powers of 2, and powers of 2, I mean, every other one is a power of 4, right? 2 squared is 4. Why do you know powers of 4? Let's see, 256, 512, 1024, 2048. Did anybody remember or know, like, computers and storage and RAM and, no? Megabytes, gigabytes, like all of them go by powers, exactly. And in the olden days when the flash drives weren't like gigabytes, when they were like megabytes or kilobytes. Anyway, it was all like, oh, a 256 flash drive or a 512 flash drive, and it could hold like 3 pictures. But anyway, like that was the measurement because of how all the computer hardware worked. Anyway, so 256, oh, well, it's not 128. Because 128 would be a power of 2, so I went the second one, 256. Yeah. But it's not random, but it seems random when you're looking at all like the computer specs. Anyway, coming back. Hey guys, now that you have a function, now that you have a point, should you be able to go ahead and plug in? But where are you going to put the 624? Just like where I put the 122, right? So that's the weird thing at the very end of homework that you guys do. There's no problem. Well, yeah, there's a problem, but you have to unravel it. Anyway, here's the weird idea I'm not giving you any word problems for. And maybe I should in a greater context of how calculus applies, but that's okay. Random guy at Starbucks is judging the math system for not giving super applicable problems in math. I'm like, they can't understand the ones that you're trying to explain to me. Anyway, there's this guy that sits at the Starbucks on Balboa and Rinaldi-ish. Anyway, Bridget and I have been going there a little bit and doing work because every now and then I was helping her on calculus. And then he heard us doing calculus. He's like, is that calculus? Oh, that's so much fun. And then he did like, well, he's a student, but he did like, what do you do? I think he did math, and then he changed to business. And then, well, it's like grad school changing, not like got an undergraduate degree and then, but anyway, then he went business? No, somehow he was in technology for a while. Anyway, so he has a lot of experience, but I think he's settling now with some sort of like, I don't know. I saw like stock market projections on his screen at one point, and I was like, okay, well. But, so he sees a lot of further application of calculus that I don't even see because I never went into a lot of those fields with econ and finance and technology as far as the depth that he went. But anyway, so there are more applicable problems than like, how do you do a fourth root of 624 and make your friends go, wow. But anyway, it's still kind of cool. Coming back. This is somewhat practical and it's somewhat useful, just the AP didn't cover it, so you guys don't have to stress about it in homework, but let's at least do one example in our notes, okay? Measurement error, how far off? Measurement error, how far off? Oh my goodness, chem labs? Anyway, do you ever measure things? Do you ever have to think about error? Okay. Percentage error. Percentage error we could think about as delta y all over y, which could be approximated by, we just said about how delta y could be dy. So dy over y. If you think about dy approximating delta y, how far off you are in regards to the whole. So let's say something that you measured was, I don't know, 7 inches, and you were 1/10 of an inch off. Were you super far off? No. But let's say something that you measured was 2/10 of an inch, and you were 1/10 of an inch off. It's a big difference, right? So that's the idea of percentage error, like based on the measurement that you're taking, how far off you are, and what does that mean? What impact does that have? And measurement error itself, we're just going to say as it depends on whether you're talking about the initial or the output. We can say the input error is going to be delta x. The output error is going to be delta y, which you might not be able to actually find, so dy can help us with. Okay, here's what's going on. The radius of a sphere is measured within, or with a percentage error, I apologize, of plus or minus 0.04%. So pretty close, right? Based on whatever accuracy or precision, ooh, those words mean different things, of the measurement tools. but they know it's within plus or minus 0.04%. Estimate the percentage error of volume of the sphere. Why is this important? If you measure something and you're a little bit off and you use it for something else, what might happen? The error might compound, right? It might get bigger. And so it might have devastating effects where it wasn't so big of a deal if it just had to do with this one measurement, but it might make a big difference in looking at the whole thing that you're using it for. So in this one, well, wait a minute. Volume and radius? Are they expecting me to have some sort of formula that relates the... Okay, V equals 4/3 pi r cubed. V equals 4/3 pi r cubed. Measurement error would be how far off r would be, the error that's going in, versus output error, the error of volume coming out. But they're not asking us for the actual, like, what was the actual measurement error. They're asking us for percentage error. So we're going to actually think about delta V over V. But this could get really complicated really fast. Because delta V over V is going to be some sort of, well, we could plug in the 4/3 pi r cubed. But what do we plug in for delta V? Before we set this equal to, well, don't even know what to set it equal to. Where do I plug this guy in? Percentage error? So maybe before we start going into the V's, maybe we need to think about what we've actually been given. All right, so what were we given? We were given the percentage error of the radius, not the volume, of the radius. So percentage error of the radius, we could say delta variable over r is equal to, what do we have? And if you guys remember back from dy and the delta y on the page before, since r is my independent variable, I can actually, don't need to stress about that one being off. Delta r and dr are the exact same thing, like delta x and dx are the exact same thing. So we could say delta r over r is equal to that. We could also say this is equal to dr over r. And who do we want to solve for? Delta V over V, but the problem is we don't have actual measurements to plug in and actually try to subtract two V's, so we're not going to do delta V over V. We're going to approximate it, which is what we're trying to do, estimate, with dV over V. Now hold on, kiddos. What do we need for dV, just like we would need for dy? A derivative. So we're going to go ahead and say, okay, fine. dV dr, or dy dx, is going to equal, bring down the 3, we get 4 pi r squared. You guys tracking on that? 4 pi r squared times dr. That's going to be dv, and then who's v? dv, I solve for the derivative, and I multiply by dr. V, just that guy. How on earth can I use the clue to solve when I have no idea the actual measurement of the radius that they did? All I know is how far off they were. How can I plug this guy in? Set what equal? Isn't he basically just a clue? I had to kind of make my own formula using what percentage error actually is talking about as far as the differential over the original. I could take dv by taking a derivative. I could take v by taking my original formula. But how do I plug this guy in? Oh, wait, there's a dr. And what else? There's an r if only I would switch this up to be r squared times r. Is that okay? Now can I substitute for dr over r? And what do I end up getting? 4 pi r squared all over 4/3 pi r squared times plus or minus 0.04%. Wait, what can I do with these guys? Don't the r squareds just reduce? Don't the pi's just reduce? Don't the 4's just reduce? What's left? A 1 over 1/3. What's a 1 over 1/3? And what's 3 times 0.04? Does the error grow when you plug it into volume? Yep. By how much? Well, your volume is going to be within plus or minus 0.12%. Using what? Well, that's an approximate for the percentage error, but it's just the idea of you don't necessarily need to have the actual measurements themselves and be able to plug in and solve by hand by subtracting the 2 measurements, etc. Because the problem is, if you were to subtract the 2 measurements, you would need to know the perfect measurement and the one that you measured. Well, if the one that you measured is off, you don't know exactly what the perfect measurement is. You know a range within which it's going to fall. But it's impossible for us to actually know the perfect measurement, the delta over V. It's impossible for us to know what is the actual distance off. We just kind of know the range. Unless it's like a lab where it's like, well, the number should be this, and you guys got that. Okay, well, scientific method has found what the number should be. But usually when you measure, you're like, well, I think I'm within this, so that was nice. I did not give you guys those problems in homework. We're going to go ahead and grade section 3.7 tomorrow, because a lot of you guys didn't finish it because I gave very specific advice based on thinking I gave you word problems when I didn't. Oops, oh well. But from your recollection of homework 3.7, I technically have the book up, but I also have the book open. Is there anything real quick you want to ask me that you don't think today covered? 25. Anybody else have a number just off the top of your head? They're like, ooh, yeah. Besides 36, don't worry, it's the picture one. I'm sure we'll go over it. Do the best you can on it. Oh, yeah, 25 was the picture one, too. Okay. Patricia. Okay. With the chart, you were making, for the whole chart, one tangent line using 232, using the point they gave you. One tangent line with that C, F of C. And then the chart was saying change the A's that you plug into the X spot. So how's the tangent line go for this one? How's the tangent line go for that one? You're getting values, plugging into, they call the tangent line T, and BC, we call it L. It's still the tangent line. So what you're doing is you're plugging into the tangent line and plugging into the function, and hopefully you're realizing the farther away I get from the point, the more off the approximation. That's all they're trying to show you. Does that kind of make sense? So that's why they're having you use it for different values, because then you should be able to see that more error as the tangent line diverges from the curvature. Okay, let me freeze the screen. I'm going to go ahead and go grab a picture of number 25, because, yeah, Thomas, that one is a little weird as far as what they give you. It's even weirder than some of what we did today in class. Oh, that's right. You guys are juniors. Oh, you're cute. I forgot about that. Ruth, have confidence in who God's made you to be. All right. What?
They played Crossroads yesterday and LeBron was there.
Are you serious?
I'm dead serious. Our Heritage middle school basketball team played Crossroads, and Bronny Jr. and LeBron were both there. Really? Yeah.
That's crazy. Missed out on that one.
It's ridiculous.
Oh my gosh. All right, guys. Hopefully you have the notes down because it was pretty quick. Thomas had a question about 25 because it's super weird and awkward as far as the wording. But do you guys see a point of tangency? Yeah, I do, right? So couldn't we, wait a minute. What do we need? It's awkward because they didn't tell us who f is. Could it be like a logarithmic function? Sure. Could it be like a square root that's been shifted down and over? Sure. I have no idea who it is. So how on earth are they expecting me to be able to make a tangent line if I need a y for a tangent line? Oh, I have it. And an x for a tangent line? Oh, I have it. But what don't I have? This is all, these are my a's I'm going to go plugging into the x spot, right? But who do I need? But I don't have a function. I can't take a derivative and plug in 2 if I don't have a function. But what did they show me? So what do they expect me to try to do? Well, this is really just a, what is the slope approximately? Well, I guess if you go up 1, right? And then go over, oh. Doesn't it kind of look like up 1 over 1? Approximately. They told us to approximate, to estimate, to approximate from the graph. Well, I see a tangent line. Looks to be about up 1 over 1. Sweet. I'll put in a 1. Ha-ha! Now what? Plug in 1.9. Doop-doop. Solve. Plug in 2.04. Doop-doop. Solve. Dun, 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 dun. I guess you could use the 0.10. Eurus is saying, couldn't we have seen that as a point and then done rise over run? True. You could have done rise over run from, that's probably a better way. But rise over run. I just kind of rised over run myself, but yeah. It looks to be hitting at 1, 0, so you could use those 2 points. So I'll go ahead and rise over run. You guys didn't know that was a verb, did you? There you go. Boop, boop. We'll go down there. What is going on with L'Hôpital's? Have you ever plugged into a limit problem? Plugged into a limit problem? You're welcome. Chapter 2. Plugged into a limit problem. Isn't that how we find limits? Try to plug it in. Have you ever gotten a 0 over 0? And didn't we have to do some sort of algebra to keep going? Do you remember what some of that algebra was? Multiplying by a conjugate for square root, simplifying complex fractions by multiplying top and bottom by whatever the stuck denominators were, foiling everything out and combining like terms and factoring and reducing. 0 over 0, there's a hole, and we need to reduce out the shared discontinuity. Infinity over infinity, we ever had that? Yeah, we did. Every time we were thinking degree tests, we were going to infinity, and sometimes we had x's on the top and the bottom. So if we plugged in, it would have been an infinity over infinity. And so we used a degree test to help us with that. Infinity minus infinity, it's 0. No, it's not. Degree tests, even though one guy is going to infinity and the other guy is, what if the degree of the bottom wins? He's an x squared and he's an x cubed. That's going to 0. Not going to 1. Same thing here. What if that's an x squared and that's an x cubed? Who's going to win? That guy. But what if that's an x cubed and that's an x squared? Here's the problem. We don't know who's stronger. Now, these ones kind of make sense because we've kind of talked about them. And depending on who's stronger, well, I guess if that guy's stronger, it's positive infinity. If that guy's stronger, it's negative infinity. If they're tied, it's 0 or some sort of ratio. Those ones make sense that we get confused on and don't exactly know how to answer. These ones, you might think there are answers and there aren't. 0 times infinity, we don't know. 0 to the 0, no. 1 to the infinity, we don't know. Infinity to the 0, we don't know. I know 5 minutes, I don't know why they're doing it. Here are some things we do know. Here's some conclusions we can make. Before we go talking about the indeterminate ones and the ones that we can't decide as is, and we're going to have to do something extra to figure out, especially with the limit, because infinity is not a number, so somehow we're going towards infinity. X is approaching infinity, hence why it's about limits. Here's what we do know. Positive infinity plus positive infinity is going to be positive infinity. An x squared plus an x cubed as I go to infinity will be infinity. A negative x squared minus an x cubed as I go to positive infinity. A negative positive will still be a negative infinity. 0 to the infinity, now this one's weird because it looks an awful lot like these guys. 0 to the infinity truly is 0. And 0 to the negative infinity, wait, wouldn't that be 1 over 0 to the infinity? 1 over 0? Oh, 1 over 0, top wins. That would be going to infinity. Anyway, there are ones that we can't decide and ones that we can. But what do we do with the ones that we can't decide? Are we stuck with algebraic stuff like conjugates? Are we stuck with degree tests and we can't do anything else if it doesn't match the patterns that we've already seen? That's a horrible thing in math. So here's something cool for us to see. What are you able to do coming into this section the old way? What are you able to do coming into this section the old way? Plug, yeah, and if you do plug it in, you end up with 2 minus 2 is 0, and negative 1 plus 1 is 0. And how would we keep going? You could have done anything in this form over a polynomial by doing what? What am I doing? Polynomials, you should know how to factor. Because the 0 over 0 means there's a shared factor, and then we can go ahead and, you guys remember somewhat, right? Factor, get rid of the whole plug-in. A polynomial over a polynomial, I don't mind a 0 over 0. I don't mind a 0 over 0. But what if we had something like the limit as x approaches 0 of e to the x minus 1? E to the x minus 1 with 0 plugged in. 0. What's this also? But how do we keep going? Can we factor this in L'Hôpital? This one, going to infinity. It's like a horizontal asymptote degree test. Degree test, top and bottom are tied. So what's the final answer going to be? 3 over 2, right? But what if I was to give you something like the limit as x approaches, I didn't think this very well, did I? Infinity of, oh, you won't be able to do that one. X to the power of 16 all over e to the x. Infinity over infinity, right? But with my infinity over infinity, because any infinity greater to the 16th is getting bigger, and e to the getting bigger, but who's stronger? I can't tell it as easily as degree tests. L'Hôpitals. What could we do before? No, there are e's. We couldn't have done that before. Well, hold on. What happens if you plug in? 0 over 0. But what could we have done back when we first did this? Couldn't we have factored a difference of squares if we had seen it? Sorry. So just because there's an e to x doesn't mean it needs L'Hôpital. There could be a deal with it pretty quickly. And then e to the 0 plus 1 is equal to 2. Maybe there was a way to deal with it, but we just saw an e to the x one that we didn't know how to deal with. Actually, 2 of them. Wait, how would we have done this one? Ooh. This one. We're going to have something new to keep going. It's called L'Hôpitals. What I want you guys to do is take a picture of it and have it ready to use tomorrow. Finish up section 3.7 tonight. Take a picture of L'Hôpital. L'Hôpital says there's more that you can do that you didn't even know. Bye. Oh, there are derivatives? No wonder BCers couldn't teach us L'Hôpitals at the beginning of the year. Bye.